Hello everyone, welcome to the last Tuesday of the DataXDays series. Today we're welcoming Niall Turbitt, data scientist at Databricks, who's going to talk about parallelizing pandas with Apache Spark. So Niall, without further ado, it's your turn.
Where I'm going to be taking us through an overview of Koalas. So Koalas is an open source Python package that implements the pandas API on top of Apache Spark. Just before we kick off, and I will be bringing this GitHub back at a later stage when we're going to go through the demo. But just to kick things off, a little bit of background on myself. My name is Niall Turbitt. I'm a data scientist at Databricks. I work on the professional services and training team at Databricks. So with that, my time is split pretty much half and half between working with our customers to build, deploy machine learning solutions at scale. And then on the other side of things, I also work with our customers and external users to upskill people on data science and machine learning with Spark, delivering training classes. So just to set the scene with what we're going to cover today. So I'm going to kick off with a brief primer of kind of a comparison between pandas and Spark, discussing their origins, having a brief look at some code comparisons, then exploring some of the justifications for the Koalas project. So why was the project conceived? What are some of the issues that the project seeks to address? Then also going to discuss how Koalas is implemented. So I think this is what a lot of people will find interesting, is that how the Koalas project seeks to recreate that pandas API, but on top of Spark. Also going to go through a very quick demo, highlighting some pitfalls that you could potentially run across with Koalas, but really highlighting the similarities between the pandas API and the Koalas API. I'll then be finishing off with just a roadmap for the future. So where do we see the project going, and what are kind of the most upcoming imminent things to look out for with Koalas. So taking a step back and just thinking about the typical journey of a data scientist. So if we think about a data scientist and moving through kind of various phases through education, industry, and notably one where that data scientist is using Python. Pandas is the standard tool when working with smaller data sets. This is primarily due to its use for beginners, ease of use for beginners coming to data science, and the fact that it's also then heavily promoted via online courses, books, universities. It's only when you then start to look at larger data sets does Spark then come into play. So what is pandas? For those that haven't come across pandas before, I'm sure many will be familiar with it, but pandas was conceived by Wes McKinney back in 2008. And like I said, it's become the de facto standard tool for data manipulation and analysis in Python. Ease of use, number one, but also its deep integration into the Python data science ecosystem. The fact that we have NumPy under the hood to work with, and then having the likes of Matplotlib to do your plotting functionality, and then how you can also use pandas, preparing your data for later use, fitting machine learning models with scikit-learn. So very deeply embedded into this ecosystem and works across a very broad range of different situations. Spark, as I mentioned, is pretty much the de facto standard then when it comes to doing data science and data engineering at scale. So very much where we're in a large scale data processing situation. And it's this integrated toolbox that can then be applied, again, across a wide range of use cases, but all under the same roof. And a large factor of its popularity can be attributed then to the fact that it caters to various communities via its range of APIs, from the likes of Python and Scala right through to R, Java, SQL. Just to highlight then the differences between pandas and PySpark. So PySpark being the Python API for Spark. So when we actually look at the kind of syntactic differences between the two APIs, what is evident, especially for someone coming from a pandas background and wanting to implement the same operation in PySpark, is not inherently intuitive for a pandas user. If we just highlight here that we want to read in a CSV file called mydata.csv, we're going to import pandas as PD, the classic alias of pandas. And what we want to do is rename these columns X, Y, Z1. And then we also want to create a column X2, which is a multiplication of our X column. Just to highlight how you would then go about doing the exact same functionality in PySpark, does then highlight some of the very basic differences in the syntax. The fact that we're using Spark here to then read and infer the schema. So we necessarily have to either infer the schema or supply the schema. So what are our data types? What are our column names? Then to actually rename the columns, in this instance, what we're doing is basically calling our data frame, then calling .toData frame. And then to add that additional column on, what we're then utilizing is this with column syntax. So like I said, not inherently intuitive for someone coming from a pandas background to go straight to PySpark and know effectively what to do going to that. And this is very much the kind of key motivation for the Koalas project. So it was announced last April in 2019. And Koalas is then a pure Python library, so can be installed like any other Python library via pip, conda, or from source. And the core aim of the project then is to provide the pandas API, so that API that we saw on the left-hand side of the screen just previously, but give users then the scalability that you inherently get from Spark, but with that familiarity of pandas. So like I said, unifying these two ecosystems with that familiar API, and inevitably allowing people coming from a pandas background that seamless transition to make working from smaller data sets. And if you want to then utilize the distributed nature and power that you get with Spark, having that familiar API to work with. So just in terms of the project's growth over the last year, so as of end of May this year, Koalas had over 30,000 daily downloads, over 2,000 GitHub stars. So really displaying a lot of growth. It's gained a lot of traction as well. And it's not just committers from Databricks. So this started kind of internally from Databricks, but has very much kind of, I know in open source, in the open source way, has gathered a lot of interest from others just outside of Databricks as well. So coming back to our example and exploring the differences between pandas, but with koalas this time. And what we see is that we literally only have to change one line here. So instead of importing pandas as PD, what we're going to do is import databricks.koalas as KS. And it's really that one line difference. So rather than having to import pandas, importing koalas as KS will then allow us to utilize that same pandas API, but with Spark under the hood. So in this instance, again, KS is going to be our alias for koalas, but it's the exact same syntax, wanting to read that CSV in, rename the columns, and then create this new X2 column. So in terms of the current status of koalas, so whilst the full pandas API is not kind of 100% covered at this stage, the Koalas team itself is making super quick progress when it comes to coverage of the overall pandas API. And this is measured by pretty much just seeing the available functionality that you have with pandas and what percentage does the Koalas API have covered there. So bi-weekly releases coming from the Koalas community, in that every 2 weeks there's a new release or a new patch coming out. And so it's a very active community with really regular changes and updates, and are super responsive to if a certain API functionality isn't there in Koalas, simply submitting a ticket or an issue there will highlight to the team that something is missing there. So if you are using this and do find some functionality that you would ordinarily have with pandas that isn't there, super easy to just file a ticket. And like I said, the Koalas team are super responsive in getting on this. So just in terms of coverage itself, so series and data frame APIs from pandas have been covered pretty much 70%, 3/4 of the way there. Index and multi-index functionality, slightly less with 51%. In terms of data frame group by, we've got 67% coverage of the pandas API, 69% when it comes to the series group by, and then a large majority of the plotting functionality there. So very much through all the releases up to the most recent 1.0 release, we see that we have nearly kind of 80%, just over 75% coverage across the entire pandas API. So what are some of the key differences between koalas and pandas? And to really understand that, what we have to think about is that under the hood, what Koalas is effectively a wrapper on top of Spark. So the chief differences here come from differences between Spark and pandas. And I just want to take a moment to highlight these and how they translate with one another. So firstly, whilst both Spark and pandas have this concept of a data frame, with pandas, a data frame is a mutable object in that you can update rows or columns of that data frame in place. In the case of Spark, however, you're going to be chaining together operations against an immutable data frame or multiple data frames. So Spark data frame syntax has also then been heavily influenced by SQL syntax, and this is as a result of the underlying SQL engine. And it is this fact itself that lends to why there is these large differences in the syntax between the likes of PySpark and pandas. So most of the differences then between pandas and Spark are going to arise from the fact that Spark operations don't get evaluated immediately. And as such, Spark is inherently lazy by nature. So operations are only going to be executed when an action is explicitly called. So be that evaluating some values when calling an action or writing out to an external data source, for example. Another big difference that arises between Spark and pandas, and as a result, koalas and pandas, is the fact that Spark doesn't maintain the order of rows in a data frame, whereas pandas essentially behaves as if it's an array of rows. So where with pandas you have this inherent associated index, Spark itself, you can think of Spark data frame, I should say, you can think of as a bag of rows without any inherent order, unless we explicitly provide that order. And lastly, with Spark, we're going to have the ability to scale horizontally, and this is kind of the chief reason why people turn to Spark, is to make use of the parallelism that you get and the ability to scale out massively by simply adding on additional nodes to your Spark cluster. So this, as such, then gives us performance at scale. However, with pandas, by design, you're going to be necessarily restricted to the memory capacity of a single machine as well. And so this then brings us to the actual Koalas architecture itself. And before I get kind of under the hood of Koalas and how it's implemented, I just want to discuss where it sits in relation to both Spark and pandas. And as I mentioned, we can essentially think of Koalas as this lightweight API layer that sits on top of Spark and pandas as well, interestingly. So as such, we can reap the benefits of having the scalable advantages of Spark and all the kind of underlying goodies that you get there from the kind of Spark core, the different data source connectors that you have, the underlying optimizations such as Catalyst and the Tungsten execution that you get there, as well as having then access to data frame APIs, the SQL engine as well. So everything that we're doing with Koalas is essentially boiling down and being translated to Spark under the hood. And we'll see as well how we can very efficiently convert between Koalas and pandas and also use the functionality such as pandas UDS in Spark for a seamless transition between koalas and pandas. And this is going to be facilitated then by Apache Arrow that's utilized to do that conversion between the JVM process and the Python processes under the hood. So as I mentioned, what Koalas is essentially doing is it's this lightweight layer on top of Spark itself, and managing that conversion between Koalas and Spark itself is something called the internal frame. So this is the kind of the underlying internal structure that is used to translate from Koalas to Spark itself. So InternalFrame is the internal immutable structure then that is going to hold the Spark data frame along with the immutable metadata that Koalas requires. The InternalFrame then manages the mappings then between Koalas column names to the Spark column names that are kind of underlying that. Further as well, in order to replicate the index or multi-index functionality that you get with pandas, Koalas thus requires that we map the columns of Spark data frame representing the index to an appropriate Spark column name as well. So essentially, under the hood, to recreate that index, we have an additional column to that Spark data frame that acts in effect as that index for the Koalas data frame. Optionally as well, the InternalFrame is going to be thought of this bridge then between Spark and Koalas, but we can, like I said, optionally enable conversion between the data frame and pandas data frame as well. And I'll show us how we can very seamlessly convert between the two if needed. Just a couple of interesting points around InternalFrame and how it's implemented. I just want to demonstrate a few ways that we can that Koalas API calls can work and how that then translates to the InternalFrame and to the underlying Spark data frame. So sometimes we're going to have an update of the Spark data frame where it's not actually necessary, and we're going to require only to update the metadata of our internal frame. So an example of this would be renaming a column or setting the index by calling .setIndex on the Koalas data frame. So in this instance, what happens is that we make the API call, we copy the Koalas data frame with the new state, so it has the same internal frame, all the while pointed to the same Spark data frame. On the other hand, sometimes an API call will require Koalas to update the internal state instead of returning a new data frame. One example of this then would be where we provide the in place equals true argument that you have with pandas. So the underlying sequence of the internal frame would then look like such. One thing to note is that a Koalas data frame never changes the internal frame, but merely creates or copies the internal frame to keep it immutable. So this is never changed itself. It's either copied or a new one is created. Just lastly as well, we can, if we necessarily call something like in place equals true, what we have is that we update the internal frame to return then the underlying Spark data frame there. So a couple of instances where that internal frame gets updated, where it doesn't, and where we actually explicitly have to. But one thing to remember here is that this internal frame, as I said, is never being changed by the Koalas data frame. One important difference that's going to come between pandas and Koalas arises from the fact that with Koalas, we're going to seek to replicate that indexing functionality present in Koalas. To do so with Koalas, and this again is going to be utilizing that internal frame to manage it. But what we're going to do is create an additional column to act as that index with, that is stored in the underlying Spark data frame. If we don't specify a specific column when creating a Koalas data frame, or we don't explicitly provide one, what we're going to do automatically is attach what's known as a default index. And there are several different types of default index which a Koalas user can configure. However, each of these index types has its pros and cons, and I'll walk through some of those. But choosing an appropriate default index type is hugely important in that users can and will run into slow performance if their choice of default index type isn't well suited to the use case at hand. And I'll just walk us through a couple of instances of that. So there are 3 types of default index type available to us. First of these is a sequence index. So sequence index, or a sequenced index, is going to be used by default in Koalas, and it's going to implement a sequence that increases strictly 1 by 1. Under the hood, it's going to use PySpark's window function. However, this is without specifying a partition. And as this is a no partitioned Spark window function internally, effectively what it means is that all the data needs to be collected on a single node. If this single node subsequently then doesn't have enough memory, you're going to run into an out of memory error. So as such, unless your data is quite small, it's advised to avoid the use of a sequence where your data set is large. If your data set is large, what we want to do is distribute the index. So there are 2 flavors here. One is distributed sequence, and the other is simply distributed. Where these differ is essentially whether you want to have a strictly monotonic, well, both are monotonically increasing, but with distributed sequence, what we get is a index which strictly increases 1 by 1. However, with distributed, essentially it's implemented by PySpark's monotonically increasing ID function in a distributed manner, but it is not necessarily increasing 1 by 1. So the key takeaway here is if you necessarily need your index to increase 1 by 1 and it's large and you need to distribute that, use distributed sequence. If not, if you're not going to employ the use of that index, use distributed. Just some caveats with distributed is that what it means, and the fact that it's non-deterministic, means that you can't utilize the index with this default index type for joins, for example. Performance-wise, these distributed indexes have little penalty compared to even the sequence one. So very much heavily recommended to use either distributed sequence or distributed, especially when your data is large. So with that knowledge in hand, I think best way to demonstrate this is walk through a notebook which will highlight some of the use cases of Koalas, and I want to highlight some best practices and tips and tricks as well. Just to call out here, I have the IPython notebook at the following GitHub link. So you can go to github.com/Niall-Turbitt/Koalas_demo, which will contain both these slides, so the slide deck in PDF form, but also the demo that we're going to walk through here. So it's a really quick kind of 10-minute primer on Koalas itself. One other call out as well is that if you do want to follow along, as I am going to be doing in Databricks, you can really easily sign up to the Databricks Community Edition. It's free of charge. It's going to allow you to spin up some limited resources, but in the same kind of Databricks environment. And anything I'm going to be doing here will then be available for you to do in the Community Edition as well. So I'm just going to quickly shift to my Databricks workspace. So like I said, this notebook is available under the following GitHub, along with the slides I've just been through. What this is pretty much an adaptation of a Databricks blog post called 10 Minutes from Pandas to Koalas on Apache Spark. Just to call out some things here, we're going to be utilizing the most recent Koalas 1.0 package. And I've tested this on Databricks Runtime 7.0 ML. So if you are following along on Databricks Community Edition, you can specify your runtime. Install or conda install certain packages. So in this instance, I have set spark.databricks.conda.conda magic enabled true on my Spark cluster config. If you need to do that, do find out more information under the following notebook scope libraries link. But I'm just going to install Koalas 1.0. And I'll take us through a couple of nuances that you get with Koalas, but also mostly kind of demonstrating that we have the same pandas API, albeit with Koalas. What we're going to be doing the entire time, or for most of the time, is utilizing Spark under the hood, so anything will be in the distributed setting. Something to note here is that although this doesn't warrant kind of a distributed setting of, the data sets and kind of the toy series that we're working with are going to be small, therefore it doesn't really warrant a distributed setting. However, the key thing that we're trying to point out here is the seamless nature of converting between the two APIs. So just importing Koalas, so import databricks.koalas as KS. I'm importing NumPy and pandas here also, but it's not necessarily necessary for Koalas, but this is pretty much just to give us some flexibility here. And very similar to how you create a pandas series, so pd.series, we can create a Koalas series. We can also create a Koalas series by passing that pandas series through to Koalas, so calling ks.series. So something just to call out here, best practice. So Koalas does not guarantee the order of indices, unlike pandas. So if we see here, we're going to run this pandas series and we have our increasing index. However, we're not, because we have this in a distributed manner, we see that our Koalas series is not necessarily in the same order that we would have. Unless we did want to explicitly order, we can call .sortIndex on this. So this, we should really be using this only in instances that you necessarily need that index sorted. If you have no intention of using the index, and there's not really necessity to do this. Another thing that we can do is pass pandas data frames to our Koalas functionality to create Koalas data frames from pandas. So a couple of ways that we can do this is we're going to create a pandas data frame just as we would typically. However, one change here is then going to be changing the PD alias to KS, and it's going to do the exact same. Albeit under the hood, like I said, this will be in a distributed nature. So in any instances where your data set that you're loading into a pandas data frame isn't necessarily going to fit into memory, you can resort then to Koalas to Koalas to do that in this distributed setting. So likewise, what we can do is get the order of the indices, and these can be sorted by dataframe.sortIndex, and we see that we have our pandas data frame. We can also then sort the index again with Koalas. In order to then view the data, what we can do is very similar to pandas. We can call .head. Under the hood, what is going on here is that we're calling .limit with PySpark. So just to highlight that sometimes whenever you have a PySpark data frame, you don't have the same .head functionality. With Koalas, you then do. And we can similarly then call the describe functionality that you would necessarily have with pandas on our Koalas data frame. So this can be super useful, especially where your data frame is very large. For example, if in pandas you couldn't necessarily fit it into memory, you could call describe, get those different metrics on your Koalas data frame in a distributed manner. And again, if we want to sort our values, same API call that you would have with pandas, and we're just specifying then the column name. One functionality that does have a bit of a caveat around it is the dataframe.transpose. So where we have a Koalas data frame, we're going to call transpose on it. This will fail whenever the number of rows that we have is more than the compute max rows, and this is essentially a default which is set to 1000. Reason for this is that in a distributed setting, this is super expensive in that we have to create additional rows and effectively do a group by twice to do the same transpose functionality under the hood with Spark. You can reset this max compute rows. So we can see that we can, from koalas.config, get the set option and get option functions. Calling ks.getOption will then tell us what the default currently is. So we see that it's currently 1,000. If we want to change that, we can set it. See that we can set to others. But one caveat here is that do be careful if calling something like transpose, that you don't run into super expensive operations. Selecting or accessing data is very much similar to how you would do so with pandas. So indexing into the column if you want to then specify multiple columns as well. So nothing new from what you would have with pandas. Slicing as well. So interestingly, you can't slice you can't slice by index when it comes to PySpark data frames. Again, this whole idea that we have a bag of rows and it's in a distributed nature. However, because we recreate that index with Koalas, we can use this then to index. So useful functionality there that you wouldn't necessarily have with a PySpark data frame. Again, slicing rows as well. So we can provide both lock and ilock to our Koalas data frame. Something to note here. So by default, again, Koalas disallows adding columns from different data frames or series to a given Koalas data frame. We can enable this. So by default, this is not allowed. If I were to run this, what we'll see is that we get an error. So we can't combine series of data frame because it comes from a different data frame. However, as we were able to do with our compute max rows, we can also set a different option here that compute operations on different data frames to be true, which will then allow us to do it. However, to avoid any potential expensive operations under the hood, this is doing a join operation. We want to avoid those super expensive distributed operations that are necessarily going to be shuffling data under the hood. So applying a Python function to a Koalas data frame, what we can do is utilize under the hood the ability of Spark to apply functions in parallel across an entire cluster. And under the hood, this is what Koalas is making use of. So it's using pandas UDFs under the hood to apply any operations that we necessarily want to utilize there. So Koalas data frames is going to utilize the same kind of support that you would get with pandas. So pandas.apply, we can do our Koalas data frame.apply. In this instance, we're going to calculate it cumulative sum from NumPy, and similarly also pass in access or axis argument as well, whether we want to implement that on either columns or rows as well. Something to also highlight is that we can effectively package up native Python functions and apply to our given Koalas data frame. And under the hood, what is going on is that this is being applied in a distributed manner. So here we're just going to apply, to take in a value and to square it. One kind of tip here is to necessarily supply the return type. So in this instance, what we're doing is supplying this return type hint. So this KS, so-called series, and it's going to be a float. Reason for this being that if we don't necessarily return that or supply that return type, what Koalas will do is run the function once for a small sample to infer what that Spark return type will be, which can be an expensive operation. One thing as well to note is that this data frame.apply, whenever we're utilizing Koalas, doesn't support global aggregations. So one thing to note here is that by default, this compute, again, this setting, this shortcut limit is set to be 1,000. So for example, if we were to take our data frame and apply, and we want to get the maximum of that column, because this is within our shortcut limit. So essentially what we mean by shortcut limit is instead of doing things in a parallel nature at times, it might be more computationally expensive to utilize pandas as a shortcut. To do this, the limit here is going to be 1,000. So the fact that we're asking from our Koalas data frame, the column A, what is the max value? Under the hood, this is simply a pandas to minimize the need for an execution in a distributed setting. However, if we were to select a range of 1001, because this is going to be necessarily distributed, we see that we have this then across our entire cluster. So you'll note that this is then going to be, well, in essence, what this is doing is getting the max of each partition across your cluster itself. So best practice in Koalas, the shortcut limit is set to be 1,000, which is going to utilize pandas whenever that data set is small. However, you can change this just as we change the different defaults. However, just bear in mind that you're going to be necessarily limited to your memory that you would have. For example, if you were doing this in a Spark cluster and it's using pandas, this is necessarily being done on the driver node. So do be conscious that you can run into out-of-memory errors if setting these defaults too high. Grouping data, so similar to you would have with pandas, group by .sum, nothing kind of new there, and we can see how we can pass in multiple columns to group by multiple columns, and applying those aggregations, plotting and visualization, and this I think is kind of some of the where Koalas really shines its use and its power compared to the likes of pandas. So say, for example, I have a large data set, and with pandas, I might have to subsample. I might have to take only a very limited portion of that data set to be able to plot and visualize it. With Koalas, because we have the ability to utilize Spark under the hood in a distributed manner, what we can do is utilize Koalas built-in plotting functionality. So here what we're going to do is just creating a very simple Koalas data frame of the speed and lifespan for different animals, and we're going to supply this as the index. We see that we can get various bar plots. We can also take the horizontal bar plot. So by default, in both of these instances, and also in the plot.py, we're only taking the top n rows so that things render more efficiently. However, what you can again set is changing this plotting.maxRows. So if you did necessarily want to utilize the entire data set, we can utilize this plotting max rows to set different limits there as well. We see that we have various pandas plotting functionality that you would ordinarily have, such as this stacked area plot that we can call. We also have a line plot. Something just to note here is that for both area and line plots, the proportion of the data will be plotted, can be set by this plotting.sample ratio. So where we had the plotting.max rows, and that was 1,000 by default, we can also specify a sample ratio as well. So I've included just an available options link as well for further details there. And similarly with plot.hist. Just what I wanted to get to was some kind of workarounds. Whenever you come into some functionality that may not be implemented in Koalas, how do we then address that? And there's a few ways that we can do that. We can essentially either convert to a pandas data frame or convert to a Spark data frame and make use of the underlying PySpark functionality. With that conversion to pandas, what we can do and what's advised here is used if you necessarily want to grab the index, instead of calling .index.toList, get your Koalas index, cast it to pandas, and then to list. The reason that this is not natively supported is because it requires collection of that data to the driver. So again, this is more of a restriction to prevent people from crashing their driver if they go to collect all of that data. Some native support for pandas objects as well. So sometimes there are certain Koalas data types that aren't yet implemented, such as timestamp and well, additionally, a Koalas series can't be used to create a data frame, but in these cases, the native pandas object can be used instead to specify those data types. Just lastly, to finish up us, I'd like to leave some time for questions. What you do get with Koalas, because of the underlying SQL engine of Spark, is the ability to issue SQL queries against a Koalas data frame. So this is something you would natively get with pandas as well. And lastly, just working with PySpark, how you can convert between a Koalas data frame is very simply just .toSpark, or alternatively, you can also call .toPandas as well from Koalas data frame. Lastly, just to finish up, is then how to specify the default index type that we were previously talking about. So in this instance, what we have done is specified that default index type to be a distributed sequence, but you can obviously change that if and when is necessary. So just to wrap up with the presentation, Koalas, what's on the roadmap? So Koalas 1.0, which we were just utilizing, has been released and supports Spark 3.0 under the hood. Koalas, the most recent version of it, will be pre-installed in Databricks 7.0 by default. So very simply, to get started, all you really need is, well, an installation of PySpark, but then simply pip installing Koalas to then utilize that. All the documentation you can find under koalas.readthedocs, and alternatively at the GitHub as well. So everything with regards to setting things up, some kind of tips and tricks as well, you can find at koalas.readthedocs. And I provided some nice resources there if you do want to take a look for some further details. So with that, thank you very much for listening in. I'm more than happy to take some questions if there are any coming through.
Thank you very much, Niall. That was very clear, very interesting. Thanks for sharing. So we just launched the questions, and we can just wait a few seconds to see if any pop up on our YouTube channel conversation. Okay, so it was so clear there are no questions at date. Thank you very much, Niall.
Sorry, I'm not sure if you can still hear me, but are there any questions from anyone?
You can't hear me. Okay, well, there are no questions at date, so thank you very much, Niall, for this great talk. Thank you for sharing all this information. Thank you for being here for the last day of the DataXday month. And for people following us right now, there's another talk in 15 minutes at 6:30 with Olga Petrova, deep learning engineer at Scaleway, who will talk about semi-supervised deep learning with GANs. So stick around, and in the meantime, don't hesitate to fill in our questionnaire, which is in the YouTube comment section, to help us make a better conference for you next time and improve continuously. So thank you, everybody. Thank you very much, Niall, and see you all in 15 minutes.
Thank you.
Bye.
Bye-bye.